Hello, welcome back to 15-Minute Math. So we're going to talk about implicit differentiation today. Sounds complicated, but it's really not so bad. So first, I think we need to understand when we're going to use implicit differentiation and why it's important. So let's consider the curve described by this equation that I've got on the screen. So you may recognize this. Whoops, don't have a tool activated. This is the equation that describes a circle. With the center at 0, 0, and a radius of 3. And so it's going to look something like this. I'm sure this is going to be very lopsided. There. Oh no, I was okay until that last one. There we go. Decent enough. So there we go. That's what this graph looks like. Notice this is not a function of x. So right now we would say that this equation expresses y implicitly with regards to x. But in this case we could actually get this as an explicit relationship. So notice that if I subtract x squared from both sides, I'd have y squared equals 9 minus x squared. And then if I took the square root of either side, I would get plus or minus 9 minus the square root of 9 minus x squared. And now I've got y written explicitly in terms of x, and I could even separate these. So that's going to be 9, the square root of 9 minus x squared, or the negative square root of 9 minus x squared. So if I can express y explicitly in terms of x, there's no need for implicit differentiation. I could differentiate either one of these with respect to x, no problem. And in fact, maybe we should do that. Let's take this top one and let's find the derivative of y with respect to x. So remember, we can notate that like this, the derivative of y with respect to x. And that's just going to be the derivative of this function. I'm going to go ahead and, first of all, let's remember that we could write this like this. And so we could just use the power rule with a little bit of chain rule. So it's going to be 1/2 9 minus x squared to the negative 1/2 by power rule. And now I need to take the derivative of the inside because of chain rule. And that's going to be minus 2x. So that's kind of fortunate. So we get a little cancellation there. And so dy dx is going to equal negative x over the square root of 9 minus x squared. And so remember what that gives us. That gives us the rate of change of x with respect to y. But that only works if we can write y explicitly as a function of x. If we can't do that, we have to come up with different methods. So let's look at a different curve and think about another way to approach it. So now consider let's look at x cubed plus y cubed minus 9xy equals 0. Now, if you're curious, here's what that looks like. That's the curve that it produces. So definitely not y cannot be expressed as a function of x. Definitely not right off the bat. But in our other function, our other curve, I should say, we were able to manipulate it so that we could express y as a function of x. We just had to break it up into two different functions like so. And notice that we're not going to be able to do that here because of this term right here. That's going to kind of put the kibosh on that. So we can't approach this in the exact same way. So what we are going to do is this. We're going to suppose that we could break this up into perhaps 2 or 3 different functions of x. Kind of like what we did here, right? So maybe you could think up here, we could call that like y1 and y2. We're going to suppose that those exist for this function, but maybe we don't know how to algebraically get there. And so what we're going to do is we're just going to say, okay, so let's just pretend y is some function of x. Let's write that down maybe. Y is a function of x. and its rate of change is given by dy dx. I mean, that is literally what dy dx means, right? The rate of change of y with respect to x. And so what we're going to do is we're just going to treat y as kind of like a function of its own with that very generic derivative dy dx. And so what we're going to do is we're going to just take derivatives when we know them, and when we don't know the derivative, because it's that mysterious function of y, we're just going to replace the known derivative with dy dx. So here's how this is going to look. We're going to take the derivative of this function. And so the derivative of x cubed, no problem. 3x squared, power rule. Now the derivative of y cubed, we don't quite know it. Here's kind of how we will approach it. If we did know this derivative, it would just be 3y squared. But we really don't know how y changes with x. So we're just going to use the chain rule. And that dy dx gives us how the function y changes with respect to x. So we need that due to chain rule. And then let's take the derivative here. Notice we do have a product of two functions, 9x and y. So we do need to use the product rule. So it's going to be 1 d2, but the derivative of our second function is y. The derivative of y is going to be dy dx. Kind of that placeholder for, we kind of wish we knew what the exact derivative is. We're just going to say dy dx. So that's 1 d2. Now remember, product rule says you have to add on 2 d1. So the second function was y. The derivative of the first function is -9. And that's going to equal, well, the derivative of 0 is 0. So I just took the derivative term-wise. So derivative there, derivative there. Maybe I'll underline these in blue and that one in green. Oh no! There we go. And then in red, that was all due to product rule. Okay, and then maybe I'll use my rainbow for there. There we go. And so that's where all those terms came from. And remember, we're looking for the rate of change of y with respect to x. So what we really want to do is we want to isolate this dy dx. So what I like to do is get all the terms that have a dy dx in them, keep those on one side, and send everything that does not contain a dy dx over to the other side. So that's going to be, well, let's add the 9y and subtract 3x squared. All right, I think I took care of all my terms. I only had 4 terms, right? 1, 2, 3, 4. I still have 4 terms, so I'm good. So the reason that I group dy dx terms on one side of the equation is I have a common factor now. I have a common factor of dy dx. And so I can write it like that. I just factored out my common factor. And now since I want to solve for dy dx, I want to find the rate of change of y with respect to x. It's going to divide through by this term here. And so dy dx, or the rate of change of y with respect to x, is going to be given by this expression, which is not a particularly nice expression, but that's giving me basically the slope of the curve at any xy pair. It looks like I have a common factor of 3 running around, so if I divide through by 3, I'm going to get 3y minus x squared over y squared minus 3x. So this is kind of useful because there's a couple things that we typically like to find with functions. For example, we like to know when the rate of change is 0, and maybe we'd like to know when the rate of change is undefined, right? We're looking for sometimes horizontal or vertical tangents. Well, now that I have this expression, I can find those. For example, let's find when the rate of change is equal to 0. Well, the rate of change is equal to 0 when the numerator of a fraction is going to, when this fraction equals 0. And so let's set this numerator equal to 0. 3y minus x squared equals 0. And obviously we can't solve this, for a particular point, but what we can say is that this curve is going to have a horizontal tangent somewhere on this curve here, 1/3 x squared. And let's go over to Desmos, and let's plot 1/3 x squared. And you can see right at that intersection is where a horizontal tangent occurs. And actually, there's two intersections, right? Because there's a horizontal tangent right at the origin, and there's a horizontal tangent kind of up here. And so that can help us find horizontal tangents. And we can also find where the rate of change is undefined. When do we have a vertical tangent line? Well, let's just set the denominator equal to 0. Y squared minus 3x equals 0. And so y is going to be plus or minus the square root of 3x, and I'll just plot one of those curves so we can look at it. So let's do the positive version. So notice that right here at that intersection, sure enough, it certainly seems like we're going to have a vertical tangent. And also, at the origin again, it looks like a vertical tangent because this thing kind of loops back around on itself. And so if we have an expression to describe the rate of change, we can find where all these tangents lie. Let's go ahead and let's find maybe one more example here. Let's find dy dx for, let's find a good curve here. Let's do x squared minus y squared plus 3xy equals 1. And so remember our strategy. We're just going to take the derivative when we know how. So for example, x squared goes to 2x. If I have some function squared and I take the derivative, I know that's going to be 2 times that function to the first, but I don't know the derivative of that function. I'm just going to write it as dy dx. Here, we're going to have to use product rule. So there's function 1, there's function 2. So it's going to be 1 d2. I don't know the derivative of 2, so I'm just going to use dy dx. 1 d2 plus 2 d1. And then the derivative of 1 goes to 0. Our next step is to group terms with dy dx on one side and send everything without a dy dx to the other side. So that's going to be minus 3y minus 2x. Factor out the common factor of dy dx. And then divide through by this kind of leftover junk here. So if I divide through on the left side, I'm just going to get a cancellation. On the right side, it's going to show up in my denominator. And that gives me the rate of change of my function. So, as you may expect, if you can't write a function explicitly with y in terms of x, things do get a little bit more complicated, but there is a procedure to do it. Just remember, take the derivative when you can. Just treat y as some mystery function with rate of change dy dx, and don't forget to use the chain rule, and then everything kind of works out, at least in a semi-systematic manner anyway.